So, combining all these observations that we have been making so far, we have obtained that the variation of the action, of the Einstein-Hilbert action, under the variations of the metric, is proportional to the following quantity. It's minus 1/16 pi kappa. Well, this is irrelevant so far. d4x, irrelevant as a factor here because we're going to put it to be equal to 0, equal to square root of g, if I'm not wrong, times delta g mu nu, multiplied by the following thing. R mu nu, let me actually make sure that whether there is a square root of g. Yeah, there is a square root of g, so it's correct. So multiplied by square root of g times r times g mu nu and times the following thing, 1/2 g mu nu r minus 1/2 g mu nu lambda minus 8 pi kappa t mu nu. So this has to be equal to 0 for any small delta g mu nu, for any value of this guy. For this to be true, we obtain the following equation. R mu nu times 1/2 r g mu nu minus 1/2 lambda g mu nu equals to 8 pi kappa t mu nu. This is Einstein equation. This is Einstein equation. And it does relate geometry to the matter, to the energy of matter. Well, the attribution of this term is arguable, whether we should attribute to the geometry because it corresponds to the volume factor, or to the matter because it corresponds to the cosmological constant whose origin can be falling from matter. So it's arguable. But in any case, this equation relates geometry and energy, and that is the essential point. So our goal for during the following lectures is to study this equation and to find the solution of this equation. So, but before we go further and to finish this lecture, let us describe a few properties of this equation and few properties of the energy momentum tensor for the matter. First thing, let us assume that we are discussing the things in the absence of matter, so no matter, and cosmological constant is 0. Then this equation reduces to the following one. R mu nu minus 1/2 r times g mu nu equals to 0. If we multiply both sides of this equation by g mu nu, and using the fact that g mu nu times g mu nu is equal to 4, number of dimensions, because it's just delta mu mu, the trace of unit matrix of 4×4 unit matrix. So as a result, after multiplication, we obtain that r equals to 0. And because r equals to 0, as a consequence of this equation, we obtain that without a cosmological constant and matter, Einstein equations reduce to the condition of Ricci, so-called Ricci flatness, that Ricci tensor is vanishing. Let me stress that Ricci flatness doesn't imply that Riemann tensor is 0. Riemann tensor is not 0. This is Riemann flatness. The condition that Riemann tensor vanishes is the fact that the space-time is flat. Of course, flat space-time solves this equation. But there are solutions of this equation which do not have vanishing Riemann tensor. So there are non-flat spacetimes which solve Einstein equation without matter and cosmological constant. This is important thing to have in mind. And another point that we want to say, let us take covariant derivative of the both. Now we are discussing this equation together with this and this. Let us take covariant derivative of both sides of this equation, Have in mind that metric tensor is covariantly constant for any, even without contraction of indices, this is 0. So having this in mind, we obtain from this equation the following relation, that R nu mu covariant derivative over nu minus 1/2 multiplied by d mu R is equal to 8 pi kappa d mu times t mu nu. So, but what is standing on the right, on the left-hand side, we have observed to be equal to 0 due to Bianchi identity. At the very end of the previous lecture, we saw that Bianchi identity implies that this is 0. As a result, even if we didn't assume from the very beginning that energy momentum tensor is conserved, the conservation of energy momentum tensor is just a consequence of this equation. This equation implies that energy momentum tensor is conserved. This has some important consequences that we are going to discuss now. So, we have obtained Einstein equations of motion, g mu nu. Now we are discussing the properties of this equation. Before going on with its solution, we are discussing various forms of it, etc., etc. So, but what we have observed that if we apply a covariant derivative to both sides of this equation, we obtain as a consequence conservation of energy momentum tensor. This is somewhat similar to the situation one encounters in electrodynamics, because there the equations of motion of Maxwell equation of motion have the following form in electrodynamics, where this is a forecurrent and this is a electromagnetic tensor, which is d mu a nu minus d nu a mu. So if we apply to both sides of this equation the ordinary derivative, this is in flat space, so in Minkowski space. So if we apply d nu to both sides of this equation, as a consequence of the fact that f mu nu is nu mu, and if it is smooth, differentiable, as a result, the left-hand side vanishes, and we obtain conservation of electric charge, electric current condition. So this situation is similar to what we have encountered. But in GR, the fact that this equation follows from this has far bigger consequences for the following reason, because this equation, in part, is just some part of matter equations of motion, as we are going to show. As a result, the system of matter equations of motion and Einstein equation is overcounted, so it has more equations than necessary. So that's what we're gonna observe now. Like, let us consider more closely this equation for an example. For an example where we have a dust energy momentum tensor. For this lecture, you will have to solve a problem which shows that for the dust energy momentum tensor, dust is just a combination of particles which do not interact with each other. So for the dust, energy momentum tensor has the following form: rho of x times u mu times u nu as a functions of x. So these are vector fields for the velocities of the dust. Rho is a mass density, and is a four-velocity vector field, this guy, u mu. So in the reference frame where u mu is equal to 1, 0, 0, 0, we have that T mu nu as a consequence of this equation as a matrix has a diagonal form. And moreover, so it's not simply diagonal, it has only one non-zero component, rho. So just for the future. Now, let us apply this equation for this case. So we have that to 0 equals the following thing. Rho u mu u nu. And then this can be put to be equal d mu rho u mu times u nu plus rho u mu d mu u nu. Well, we so far don't know anything about this or that side. We just want to use identities. Let us multiply both sides of this equation by u nu. Both sides of this equation u nu. And we're going to use that u nu times u nu is equal to 1. That's just a property of velocity, as we know. And if one applies to both sides of this equation covariant derivative, d mu, one obtains the following equation. As a consequence of this identity, we have that 2 u nu d mu times u nu is equals to 0. As a result, after multiplication of both sides of this equation by u nu, we get that this side is vanishing as a consequence of this identity, and we obtain the following equation, that d mu applied to rho u mu is equals to 0. The physical meaning of this equation is actually very simple. This is just a covariant form of the continuity equation. In flat space, in Minkowski space, we have this equation. Continuity equation has this form. In curved space or in curvilinear coordinates, this equation is extended to this form. And so it's a covariantization of the continuity equation. It has a clear physical meaning. But because this is equal to 0 and this is equal to 0, we obtain that this equal to 0. U mu times d mu u nu is equals to 0. But this is nothing but the geodesic equation that we have obtained in the previous lectures. It means that as a consequence of the energy momentum conservation, we have that matter content of the dust moves along the geodesics, which means that we have obtained from this equation equations of motion for the matter, while no one never obtains equations of motion for the matter from the charge conservation. So that's an important difference that we encounter in this case. To conclude this lecture, let me describe a few more examples of the matter action. Well, let me use a different pencil. So I'm going to describe a few more examples of the matter action. Let us describe a matter action for the scalar fields. So for the scalar field, we can build up very easily invariants. Like the simplest invariance that we can build from a scalar field, it's a polynomial of the scalar field. Any polynomial of the scalar field, sum over n from 1 to n, a n phi to the power of n, is invariant. Well, but this invariant doesn't contain derivative of the scalar field. So to have dynamical equations of motion for the scalar field, we need derivatives of the scalar field. Then the simplest invariant that contains derivative of the scalar field can be built as follows: d mu phi, d nu phi. So this is the simplest invariant. Having this invariant and this invariant at our disposal, we can write the scalar field matter action as follows. It is just integral over d4x square root of modulus of g, so this is invariant, and multiplied by this invariance, like g mu nu, d mu phi, or d nu phi, like this. minus v of phi. So this is the simplest example of the scalar field action, where this is a potential and this is kinetic part. So another type of action, of the matter action, can be written for the electromagnetic fields. Electromagnetic tensor in curved space or in curvilinear coordinates, which is by definition is this quantity. But after using the definition of the covariant derivative, one can easily show that this is nothing but d mu a nu minus d nu a mu. So this is the electromagnetic tensor practically doesn't change in curved space-time or in curvilinear coordinates. As a result, we can straightforwardly write the following invariant, generally under general covariant transformations, the following action for the electromagnetic fields now. So this is again invariant, and now we built an invariant from electromagnetic tensor. G mu alpha, G mu beta. So now at our disposal we already have three types of matter actions. This one, and for the particle. So now we know everything that we need to solve Einstein equations and to study dynamics of general theory of relativity.